Okay, so we're going to take a look at section B of the energy booklet. We're going to start off thinking about some uncertainties in measurements and whether they're systematic or random. So, not allowing for zero uncertainty on a voltmeter. So zero uncertainty is when the voltmeter has a non-zero reading when it should be reading zero. So that's going to give you a systematic type error because it's going to be the same in every reading. It's going to make every reading slightly big or slightly small. Not subtracting background count rate with radiation. Again, background count rate is a constant value, so that's going to introduce a systematic error. It's going to make all of your measurements too big. Stopping a stopwatch at the end of the race is very likely to be a random type. Making judgments about when something has reached an endpoint is always going to be a random type error. Using the value g equals 10 when calculating weight, again, that's going to make all of your weights slightly too big, so it's going to be a systematic type error. Okay, so we've got a trolley being pulled from rest along a horizontal table by a falling mass. The trolley mass is 1.5 and the falling mass falls through 1 meter. What's the maximum kinetic energy? Well, that's going to be the maximum. That's going to be when it's just before the mass hits the ground. So a lot of people are going to make a mistake here because they're going to calculate the change in GP for the 0.5 kilogram mass and give that as the answer. And that's problematic because we're asked to calculate the kinetic energy of the trolley and just the trolley. So we are going to use conservation of energy. I'm going to assume no work done by friction or air resistance. But the thing is, there are going to be two kinetic energies, the kinetic energy of the trolley and the kinetic energy of the mass. But the key to this question is they're tied together, so they're going to have the same acceleration and they're going to have the same speed. So that's how we've ended up with that expression there. Their speed is the same. And then once we've got that, we can rearrange that to make v squared the subject, and gives us that number there. And we just need to times that by half m, and that will give us the kinetic energy of the trolley, which is clearly option A. Okay, so that's that one. Okay, so a metal sphere of radius r is dropped into a tank of water. It sinks at speed v and experiences a drag force given by F equals KRV. What are the SI base units of K? So the first thing I'm going to do is I'm going to rearrange to make K the subject. And then what I'm going to do is put in the units for the things we've got there. So force is newtons, radius would be meters, and speed would be meters per second. And then I'm going to clean that up into a nice form, so the second is going to go onto the top line. So a newton is not an SI base unit. So what I'm going to do is, in place of a newton, I'm going to put kilograms meters per second squared, because remember, force is mass times acceleration. And then we need to clean that up, and we end up with C as the answer. An Olympic athlete competes in a sprint race. What's the best estimate of the mean kinetic energy? So during a sprinter does 100 meters in about 10 seconds, so it's going to be at a speed of 10 meters per second. I'm going to say their mass is about 100 to make it nice and simple. Half mv squared gives you an answer which we typically give to one significant figure, and we can see the closest option is answer B. It's in the same order of magnitude. Okay, so two objects, P and Q, equal mass, are fired from ground level at the same speed. So from that first statement, what I'm taking away is if they have the same mass and the same speed, they both start with the same kinetic energy, and they're both fired from ground level, so they start with the same GPE. So the two objects have identical energy to start with. So P is fired at 45 degrees, Q is fired at 30 degrees above the horizontal. So what I've done is I've sketched those two paths they're going to have down there at the bottom. Which of the statement is correct for the objects at their maximum heights, ignoring air resistance? So kinetic energy of P and kinetic energy of Q are equal but not zero at their maximum height. Well, that can't be true because P at its maximum height clearly has more GPE than Q. But they started with the same amount of kinetic energy, so therefore Q must have more kinetic energy at its maximum height. So that can't be right. Kinetic energy of P and Q are both zero. No, they'll still be traveling horizontally at their maximum height, so that's not true either. Kinetic energy of P is greater than the kinetic energy of Q? No, it's going to be less because it has more GPE. Kinetic energy of P is less than of Q. That seems right. Q has less GPE at the top, so therefore it must have more kinetic energy to keep the total energy the same. On the surface of Titan, Saturn's largest moon, a mass of 5 kilograms, experiences a gravitational force of 6.8 newtons. What is the speed of impact on the surface when released from rest at a height of 5 meters? So the first thing I'm going to do is figure out what G is on the moon using the weight and the mass. And then we're just going to use conservation of energy with no work done. We're going to rearrange that to make the speed the subject, plug the numbers in with our value of G that we've calculated, give our answer for the speed, which is clearly option A. An object falling at terminal velocity through the air is converting gravitational potential energy to kinetic energy. No, at terminal velocity, speed is constant, so nothing is being converted to kinetic energy. GP to thermal energy, that seems very reasonable. So friction and air resistance generate heat, and we are decreasing GP, so that seems sensible. Kinetic energy to GPE, no, that would mean the skydiver was going upwards. That doesn't make sense. Kinetic energy to thermal energy, nope, that would mean the speed is decreasing, which again doesn't describe terminal velocity. Question is about using a gravel bed to stop a runaway lorry. Okay, so the escape lane was a straight line. So we've got a lorry of mass 8,000 kilograms, enters at a speed of 20 meters per second, calculates kinetic energy or show it's that value. Well, we can just plug our numbers in, turn it into standard form. That's fairly straightforward. The escape lane is horizontal, so no change in GPE, but the loose gravel provides a resistive force. And the lorry is brought to rest over a distance of 50 meters. Show the force is 32 kilonewtons. So we know there's no change in GPE, so we know the work done has to be equal to the change in kinetic energy. It goes from initial speed to 0, so V is 0. Plug those numbers in, and we end up with this number, which is also the same as 32 kilonewtons. Okay, so in practice, the resistive force provided by the gravel is unlikely to be constant. Suggests one factor that may cause a change to the resistive force and how it affects the stopping distance. So my thinking is the lorry might start to skid, which is going to change where the frictional force acts. So instead of being at the brake pad axle, it's going to be between the wheels and the floor. I reckon that's going to give you a change in mu, the coefficient of friction. I reckon that might give you a larger frictional force, which would cause the braking distance to be shorter to do the same amount of work. We could also have here maybe some of the gravel gets stuck in the wheel compartment, and that might increase friction and decrease stopping distance. There's a lot of different explanations you could come up with, but the idea is to come up with something and then explain how it affects the stopping distance. By considering energy changes taking place, explain why a lorry of the same mass and speed can be brought to rest in a shorter distance if we have an uphill gradient. Well, the key is that some kinetic energy is transferred into GP, which means the brakes have to do less work. So if you're applying the same force, that means a shorter stopping distance. Okay, so we are actually given some information about this slope. So we're told the height of the slope at which it stops. And now we've got the same force now calculating the new stopping distance. So I'm going to apply conservation of energy. We know the final speed is 0, so we put V is 0 in there. I'm going to rearrange that to make D the subject. And I've just swapped the terms around with a negative sign. Plug the numbers in to the calculation. And remember, 32,000 is acting against the motion, so it's going to be minus 32,000. And we can calculate that the distance is 38.9, blah, 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 which is about 39 meters, thus completing section